Devin, you didn't tell me, dude. Okay. So today, sorry to repeat myself, it's going to be system ID from a step transient response. The reasons are here and they're in the notes and they're posted. And I'm actually going to try to give you a better example of why it's so important to look at the time domain when I do some hand-done notes a little bit later. But all right, so Art's joke is we work in the time domain, but we get paid in the money domain. Right, so what is the, all right, to go to the ridiculous extreme. All right, so the thing is, you know, we have a function of how much time we spend at work, right? What is our Laplace, what is our transform to put that into the dollar domain? So instead of the S domain, the dollar domain. So Fourier, it's just complex. I mean, it's just imaginary. Laplace is real plus imaginary. And so what is this? The money domain? I don't know. Maybe there's a third axis there that we have to add. But that's pretty clever. So again, the first order functions are pretty easy to tell, right? And things just go 5 tau. So really, you just got to know what the gain is and how long it took to get there, and then match the shape, right? So the thing is how can I tell this is a first order circuit and not a second order overdamped? Well, it's actually right here. You see where it's straight, okay? That actually means it's first order. Now, another clue is, you know, it's not doing this, right? That's a second order. In order to have any oscillation, you have to have an imaginary number. In order to have an imaginary number, you have to have plus or minus some kind of -1, which means 2 roots, which means anything with oscillations has to be a second order system no matter what, right? But yeah, if you were to look right here, it'd be very hard to tell second order, under, or even critically damped, but it's right here. The second orders all have, and I'm going to exaggerate, they all have kind of like this, what you might call, takes a little while and then it gets going, like an S shape, all right? But starts at 0, ends up at some DC value. No ringing. There's no S-type curve. And it'll be easier to see when I show you a second order system. So I am postulating that this is a first order system until there's some evidence to the contrary. Because we're trying to identify this system based on some measured data, right? And I'll just leave it at that, right? So how would we extract the gain? Well, you just look at the DC part up here, right? If I put in 1 volt and I'm getting out 2 volts, well, I'm just going to get, that's a gain of 2, right? How long does it take to get there? Well, I just come up and measure the time. And yeah, it's subject to a little bit of interpretation, right? Like what is that 5 tau? Well, I think if you had a range of that, or maybe even here, I could accept. So let's say you're on an exam and you put down 5 tau as 10 seconds, right? But really, out here is wrong because it's been relatively constant for quite a long period of time. And of course, out here is wrong as well. So in this case, 5 tau, I don't know, 14, right? So what's tau? 14, or no, what did I have there? I was at, it's 13.63 divided by 5. That's tau. Done. right? High pass, because you put in a step, oh yeah, there's a lot of change here, right? In the frequency domain, or S domain, it's 1 over S, but look at it, it's constant. So after some point, it's a DC voltage. So what are we getting out? Some kind of DC voltage. I'm passing the low. And yeah, I guess I have to go and fix all these links. Okay. So again, here's another example. And again, it's how long does it take to get close? Well, 1.9, 1.99 is practically 2. And I'm saying, oh, it took about 10 seconds. So the gain is 2. That gives me the extraction. All right. But yeah, doing it on the homework when I give you something by hand or an exam, yeah, our answers are gonna vary a little bit, but that's okay. Because in some sense, this is like a job interview question, right? So I am preparing you for a job interview. So if anyone were to say we do nothing to help you prepare for job interviews, I would disagree. Yep. You just round it, okay? Bless you. Right. This is like this quick thing done by eye. Hey, how long? Oh, it's taken about 10 seconds to get up there. All right, tau's about this. All right, this is not we are, and so this it's kind of important, is that while yes, for H of S, I'm really trying to extract the best omega naught, right, for a system. And with the Bodhi plot, omega naught can be found pretty clearly, right? Wherever, first order, wherever it's minus 45 for the low pass, plus 45 for the high pass. This is, like I said, just to look at it, it's very hard to extract. We're just trying to say, I thought I was testing a first order low pass, but damn, I'm noticing some ringing. Well, something's wrong, right? You got to go fix that. That's how to use what I'm teaching today in context. Does that might sound like I'm hand waving, but no. Yeah, because 5 tau isn't really 0, and in fact, it's always increasing. It never really becomes constant, right? But it's an engineering approximation that, hey, did I put in, for me, sometimes it's easy to make a mistake pulling the right capacitor value out of a part cage. The resistor's easy because the colors are right there. But what I have found, at least around here, the capacitors are mixed up in the bin all the time. And unless you verify it, you could be getting the wrong thing. So if I do this and I'm getting 20 and I expected 10-ish, hey, something's wrong with my system. It's good enough for debugging, right? And again, the phrase by eye is telling you the level of accuracy. Now, if I were to give you a file, oh, well, how do you extract it? Well, that's actually kind of hard to extract this kind of, to actually curve fit this is somewhat difficult. So what you do is you get rid of the constant. So now you have a decaying exponential. You also take the absolute value because of about what I'm about to do next is that then when I take the log, I can find the slope of this and get exactly, I can extract it very carefully. But again, if I'm going to be doing all that, maybe I'm actually going to use the step and try to use the FFT to get HS directly. Because yeah, I guess it's another way, right? Come up with this, come up with the equation, 1 minus e to the minus tau, and then use the Laplace transform to come up with H of S. Second order systems. All right. This example is super involved, and I don't mean to pass things over, but here's a second order system. It backfits to this kind of equation. You use partial fraction expansion, and you can get, a constant, a decaying exponential, and another decaying exponential, because second order systems can be over, under, and critically damped, right? This might be too much information, and I'm going to just briefly go over this. Here is a second order system. Notice I've got this little bit of S-curve here rather than this straight line. So I'm thinking second order. It comes to a relatively constant value, so I'm thinking low pass. But how do I extract these two constants and these two decaying exponentials, right? Well, it's involved, right? So what I try to do is have, just before I get rid of the constant, so I should be seeing decaying exponentials, right? And if I can get a straight line, right, chances are I'll be able to find at least one of those values, right? And then so on. But once I find one, so I have the DC part, I can find the DC gain. I can find one decaying exponential relatively easy because that's kind of the slow part. But then to get it to work right, I kind of have to keep guessing values to see which one will match. Okay? If you're confused, I'm not going to help you because it's confusing. What I'm trying to say is I went and did this sample and found it to be so hard that I thought it's not worth teaching, because all I really need you to do is this a high pass? Although I gave you the, how I did it, but really, is it a high pass, low pass, notch, right, or something else? Then once you know what you're looking for, well, then you can go in the Bode plot and go from there, all right? Okay, some things are best just done with an example. So what we have here is an RLC circuit, right? Zeta is the damping coefficient, right? Omega naught is 2 pi, in this case, times some frequency, 1 kilohertz, right? Then I've just set L equal to 1 Henry. Is 1 Henry realistic? No, but to show you the effects of low, high, medium, and all that, it's fine. Then, in order to make zeta 1, I have omega naught, and then C, and then to solve for R, I have 2 omega naught zeta times the inductor. All right. So this is just that transfer function for series connected RLCs, which, yeah, it's the same thing for the mass spring damper when everything is in series. Now, the beauty of this is that the high pass filter is really just across node 3. So if I look at this thing called low pass, I'm just saying it's whatever is here at node 3. High pass is actually measured from node across the inductor. So then rather than draw another circuit where the inductor is here and the capacitor is here, no, I'm just taking the voltage right off of 2 and 3. All right. Band pass, you actually take it across the resistor. And then notch is you sum the low and the high passes together. So I think you've seen me do this, and you've done it yourself, where you type in the Laplace transform in a behavioral voltage source to get the frequency response that you want of any particular filter. The problem with that is when you go to do the time domain, it sometimes just doesn't work. So in fact, if I'm going to model any kind of filter in the time domain, it's better to make up an RLC circuit, even if it's got ridiculous values, right? Because then you'll get the time domain will be correct. All right, so let's just run it. Let's just run it. Let's just run it. Let's look at the high pass, the low pass first. Okay, how can I tell it's a second order low pass? I see this little S part, okay? I see that it goes to a constant value. So a step response has a lot of change and then it's a constant input after that. So if the output is a constant value, yeah, it's probably going to be a low pass filter. First order filters are just exponential. They don't have anything going on here. Now, that's kind of as much as I can do. I don't see any oscillations, okay? So it's underdamped or no, over or critical. But what I have found is second order critical or overdamped all have this value right in this little shape. And if I just present it to you blind, you can't tell what it is. Is it critical or overdamped? So on homework and things, hey, what is the damping factor ratio? Well, it can't be less than 1, but it could be, from 1 to 10. It's second order. It's high pass. It's low pass, right? Now let's superimpose the high pass. All right. Now, a little bit trickier, but it ends at 0. Okay, so DC is being attenuated. Let's look at the beginning. It's nothing, and then instantaneously goes up to a value. Well, that's looking very high pass, right? Now, now why isn't first order? Well, look, it goes down and then comes up. with the high pass filters, you might think, oh, see, there's an oscillation. This is underdamped. But no, it goes below zero once and then comes back up and doesn't cross again. So no, it's really under or no, it's really critical or over. Now, sometimes when something is really overdamped, it doesn't go below. But this, all right, now let's look at bandpass. So bandpass filters, it rejects low frequency, it rejects high frequency, right? Well, it kind of has a, at the start, it's increasing, kind of like the low pass, and at the end, it's going towards zero, kind of like the high pass, right? And in the middle, it kind of goes up and comes down. So it's filtering, it looks like because it goes back to zero, right? It's filtering DC. Because it does not instantaneously jump to the step value, it's filtering low frequencies. So if I'm filtering low and I'm filtering high, and notice, how do I tell that it's filtering high? I'm looking at the longest time period. How do I tell it's filtering high frequencies? It's at the beginning of the graph, right? And then in the middle, it comes back up and goes down. Okay. Now, notch. What? So look at, oh, is there a, no, it's not a question. So look at long period of time. It's passing the 1. Remember, this was a 1 volt step. So it's passing DC. Okay. But wait a second. Over here, it's instantaneously going to 1, just like the high pass filter. And rather than getting bigger in between, it's going down. Well, that's a notch. All right. So yeah, it's like this logic game. Like, is it doing this? Is it doing this? If this, then else, then it's this, right? Now, let's make the damping coefficient, large. Okay, so because the damping coefficient is larger, yep, I have to increase how long I am going to simulate for. Okay. Now I probably have to. Now, you really have to look hard, but you can see there's this little change in slope at the beginning, making you think, yep, that's a second order filter. All right. And if I run it for a long time, well, you can't really tell, can you? So you could say first order, low pass because it goes to DC. It looks like a straight line, and you'd have to zoom in to tell. Oh, it's second order. So what becomes important is that you justify your answer. It's first order because it looks like a first order shape. All right. Let's look at the high pass. Well, it decays so rapidly, right? It's kind of hard to tell what's going on, so we have to zoom in. But notice, okay, it goes up, comes down pretty rapidly, and it doesn't cross at all, right? By eye, it would be pretty hard to tell that this was a first or a second order circuit. And the thing is I set the damping coefficient to such a big number that the poles are so separated and one acts so fast and the other one acts so slow that, yeah, you might make a case that you could be able to ignore that, right? Let's look at the bandpass. All right, so it starts at 0, it goes up, but it doesn't go instantaneously up and then slowly decays. Okay, bandpass. Notch. It kind of had, the beginning looks like a high pass and the end looks like a low pass. So that would mean notch. All right. But that's like with this, kind of a large value of that. But, those two poles are a lot closer together, right? But even with a damping coefficient of 2, yep, you can see that it's not crossing at all. But remember, like what I said, a damping coefficient of 1. What about 1.5, right? Okay, it's still not, it's, oh wait, where's the high? I need to see the high. Well, we'll just see everybody. See, even here, the high pass does dip once, even though the damping coefficient is certainly overdamped. And even at 2, if I recall. So see, even at 2, the high pass goes below and comes back up. And yeah, well, what about 0.99? Oh, that's underdamped, definitely. And yeah, mathematically it is. But look at the low pass. You can hardly see any overshoots, right? But with the Butterworth, like a typical value for filters can be a damping coefficient of 0.65, right? All right, there we go. All right, here's some overshoot. Notice how the high pass, it goes below, goes back up and comes down. That's a definite overshoot. All right, so that you could reasonably, with this one, I guess what I'm saying is when you're underdamped it's really easy to tell that you're very underdamped. And so when you're doing the homework, yep, it's going to be like you're estimating, or based on the evidence, what do you see? And I would say on exams, I try to be pretty obvious, right? Is it first? Is it second? Is it band, notch? Things like that. Okay. But there was some problem with the homework where it kept saying, look at this Bodie plot. I had fixed it, but I guess forgot to update it, and I'm sorry. It should be fixed now. All right. So, here's a step response. First order low pass. Or I guess it's not I guess it's not a whisper to those that right? So, can it be first order? Can it be second order? What is the DC gain? What is tau if one can be found, right? So these are just don't kill yourself over it, right? Because we're just looking for estimates of, is this really what it is? Is this really a high pass filter? So that when I go and do my Bodie plot analysis and click high pass, that I'm actually going to get the right value, right? Or is my extracted model going to make sense? But see, here's something with a lot of oscillations, right? So it's obviously underdamped. All right, still. This one's a little bit tricky, okay? Because it's just a sine wave. Huh? Oh, wow. Can you say that? Oh, okay. I will answer your question, but I want to do it with the notes. But before we do that, yeah, guys, it's time to start reviewing for the final, right? So here, question 12. These are things like that you could see on the final that you should already kind of know, right? Plot. Okay. Yeah. All right. So we're just trying to, because yeah, there's some skills we haven't done in a long time. Now, let's just have a quick review. All right. Here is our S plane, right? I can have two poles out here, and it will be stable underdamped, right? stable, but more underdamped. Oh, okay. I didn't. Um, I was thinking of. So the question is what if? I guess the thing is if, as we're going to find out, right? If I keep these poles on the 45, it's the same amount. Okay, and when we look at the Butterworth filter, that's kind of what's going on. So I guess under those conditions, yeah. So so for these kind of red poles, are they mathematically stable? You know, we can say yes. No, nope, I haven't showed. These could all be so close that they're all really unstable. But let's say zeta equals 0.7, right? Stable. Engineering would say stable. The green, zeta equals 0.65. Math would say stable. Engineering, yep, they would say stable. Because over a little bit of overshoot's okay, right? Blue. Zeta equals, zero 0.1, right? Mathematically, stable. Engineering, you're going to hate this. Maybe not. Okay. And I didn't realize it. Yeah, the first time I taught, yeah, as a practicing engineer, basically something that's really underdamped is effectively unstable. And so rather than those rules of stability, right, where, we have the polynomial s to the n plus da 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 da, right, where no sign change, right, no missing power of s, right. Um, those are the mathematical stability criteria, right? But I would also put in underdamped, which, yeah, I think math folks had trouble with that. And there's something called phase margin, all right? And Now, what if HS is 1 divided by S plus 1, right? Well, for the magnitude of S a lot bigger than 1, right, the phase is going to be minus 90, right? If you look at that Bode plot, that's the magnitude, right? And then the phase is going to go from 0 to minus 90, right? And this is omega naught at 1 radian per second, right? So this system, I have a margin of phase of minus 90, all right? Now, when I put it in the feedback loop, right, it's negative feedback, right? But if I delay this, I guess if GS has minus 90 of phase, well, this had minus 90, this had minus 90, I'm at minus 180, minus 180 is plus 180, which is positive feedback, and now it's unstable. Okay? So in engineering, yeah, so mathematically, I have 90 degrees of phase, right? I'm great. But the system, so what if this system is giving me minus 80 degrees of phase or minus 70 degrees of phase? It will start to oscillate, right? And let me put it this way. Let me draw a Salin and Key low pass filter. Let's say I design this whole filter, right? That then if my R's and C's vary, right, I could get more phase than I expect at a certain frequency. And so the thing so because it seems to me that excessive oscillations are so to be avoided, they say, no, you want to make sure that you always have, when you design a system, you always have 60 degrees of phase margin, meaning if your feedback loop adds 60, you'll still be stable, right? Or that, and this is a little bit more than I wanted to go over today. It's more, I think, in 132, they should talk more about phase margin. There's things like Nyquist criteria or Nyquist plots to see how unstable you are. And there's others. All right. But that's kind of what 132 is about. So the question is, you know, it was kind of like how close to unstable can you get, right? Well, mathematically, you can be 1 nano-unit away and it's still stable, but the time, I think so the question, can I just say that that is an extremely underdamped response? I think, was that your question? Okay. So my answer to you is, yeah, you could. Now I happen to know what I put in there, right? Um, but yeah, what if it takes an hour before you can see any change in this, right? And those oscillations, or like, what if this is really like the this voltage responds to some position of direction of which way the car is going. I do a step response of the car. I just yank the steering wheel just a little bit. But my position, my direction is changing back and forth, back and forth, back and forth. Well, no, that, in fact, any overshoot you're not going to want. People are going to call it unstable. Now, for exams, right? Right, for exams, the stability. No, use the criteria. Okay, but yeah, that one with the sine wave, you could answer it more than one way. You just justify it, right? Just because I know what I put into Python doesn't mean it could be interpreted more than one way, right? But just, yeah, use those stability criteria when we're talking about instability. And yeah, fighter airplanes are actually designed to be a little bit unstable. And the pilot actually, as the feedback loop, has to provide the stability. Now, commercial aircraft are designed to be very, very stable so that almost no matter what you do, it's going to come back and try to fly straight. All right. But like, how could you tell? Now, it might seem, oh, you're really confusing me adding all this. Now we're talking about phase margin out of nowhere, right? But if I have two poles, right? Well, or sorry, if I'm at minus 45 from here, right? Minus 45 from here, right? Well, then there's your phase angle, right? So if you're here, yeah, you're getting much more phase. So it's easy to find, actually. And you kind of already know it. Now, I don't know if I answered your question, Josh. Oh, I'm just, um, I, I'm talking intuitively today. For the Butterworth conditions, You see, there's actually a circle, and I'm just showing you these two things. But because there is a 90 for the whole thing. Yeah, from here to here is like 90. But I don't. No, I'm not going to answer any further because I don't want any. I don't know. I've been getting comments lately. Not from you guys, but yeah. Fourth, so omega naught, and let's just say that's 0 dB and that's 3 dB. These two numbers plus the DC gain go into zeta. 0.707, no, it doesn't peak. It's totally flat. That's the whole point of a Butterworth filter, and using 0.707 as a damping factor. Okay. So now, yeah, if you see a Bodipa low pass filter that does this, oh yeah, that's definitely underdamped, right? Critically damped, right? Omega naught would actually be at -6 dB from wherever it was, all right? Then that is actually, in fact, critically damped. I only mention it because you gotta extract all three of these to come up with zeta. And some folks just say, oh, it's flat. That's always got to be 3 dB. So then just calculate it. No, it changes. Okay. And to go back to that low pass, so a second order overdamped has two exponential decays. All right. And remember what I said is if one was a lot bigger than the other, then it won't matter. And so if omega 1 is a lot bigger than omega naught, e to the minus omega 1t decays very quickly in comparison, right? So one minus e to the minus omega 1t, right? That's the low pass step response. But what would be missing? The plus e to the minus omega naught t, right? Now it's odd because this is plus, but really this plus is what gives you that S shape. And this is, this omega naught, nope. This omega naught is making the system decay so slowly that this kind of drops out, right? If this is a lot bigger than this, its 5 tau is a lot smaller than this 5 tau. So at long periods, you're going to get this. And so that's why when I say if one of these is a lot bigger than the other, it can appear like a first order, because this could could decay so quickly, right? So what if, you know, tau 1 is so much smaller than tau 0, right? This decays, this time frame, if it's 100 times less than this, well, if I plot it for a second and this is a hundredth of a second, but I have to plot out for 5 seconds, you just can't see it on the same time scale. All right. What we're going to go over later is we're going to get back into like where these filters come from, and I keep drawing this, you know, imaginary real axis, and I keep putting things here like this, or zeros, you know. We're actually going to get into using this to kind of find out where like the Butterworth filter comes from, or the notch filter. You can put zeros on this axis and then put poles really close, and then you can get a notch filter very easily. All right. And just remember, this axis right up here is the Bodie plot. We just have to take the log of everything. We take the log of the magnitude, the log of the frequency, and we just calculate, you know, as omega gets bigger, we just calculate the magnitude and the phase of these poles. And I've got a Python thing that actually tries to plot out the poles and zeros in 2D. And when these get close, right here on the axis, it's going to infinity, right? Because the pole is where the transfer function goes to infinity. So if a pole is way out here, it might be going to infinity out here, but not near the j omega axis. All right. That's even another way to look at it. Let me just get out of that so I can see. Any other questions? Just so you know, I do have a video and a document entitled Learning Objectives of 110. And I tell you, like, homework by each assignment, by each homework, by each quiz, by each exam, exactly what you're supposed to know, right? So there shouldn't be any shock as to what's going to be on the final. And I know I've harped on the homework a bit, and unfortunately, yeah, if it's not in, it's not in, and I have to follow the green sheet, which is the contract. But really, doing those homeworks that look like exams, probably a really good way to study. Even if, so I get the question a lot is, I didn't do the homework, should I still do it? Oh yeah, because that's how you're going to do well on the exam. And yep, there might be a temptation to just read the homework solutions and the previous exam solutions. But without doing the homework yourself, even getting it wrong, right, you won't be able to understand that. So really, I really just want you all to succeed first time through. Okay? If you get stuck, email me. So without any further ado, I guess I'll just, is there any questions? Alrighty. Take care.